Section 4.2 talks about binomial distributions. So we have something called binomial experiments, and it says in some experiments there are only two outcomes, success and failure. A binomial experiment is a probability experiment that satisfies the conditions. Number one, the experiment is repeated for a fixed number of trials where each trial is independent of others. There are only two possible outcomes of interest for each trial. The outcomes can be classified as a success or a failure. The probability of success is the same for each trial, and the random variable x counts the number of successful trials. So we have some symbols here, and it says n is the number of trials, p is the probability of success of a single trial, q is the probability of failure in a single trial, and notice q is going to be equal to 1 minus p, and x is going to count the number of successes in n trials. So either no successes, which would be 0, 1, 2, 3, so on and so forth. Okay, so the directions here say identifying and understanding binomial experiments. Decide whether the following is a binomial experiment. If it is, specify the values of n, p, and q, and list the possible values of the random variable x. If it's not, explain why. Okay, so the first part here says we're going to take a multiple choice quiz that consists of 10 questions. Each question has 4 possible answers, one of which is only one of which is correct. To complete the quiz, you randomly guess to answer each question. The random variable x represents, the number of correct answers. Okay, so let's see if we can figure this out. N. Remember what n stands for, the number of trials, right? So how many questions do we have? We have 10, so n's going to be 10. P, the probability that we get this correct, okay? So it says each question has 4 possible answers, right? So the probability that I'm going to get it correct would be 1/4 or 0.25, okay? Q is the probability that I fail, that I don't get it correct. So if the probability that I get it correct is 0.25, the probability that I get it incorrect would be 1 minus that, 0.75, okay? And X is going to be the number of successes in n trials. So I have 10 questions, right? And we're going to randomly guess. It's possible that I guess every single question incorrectly. Or it's possible that out of all the 10, I only get 1 right, or 2 right, or 3, or possible that I get them all right, right? So this would be binomial. And there's my n, p, q, and x. Okay. Now let's go on to number 2. It says a surgical procedure has an 85% chance of success. A doctor performs the procedure on 8 patients. The random variable represents the number of successful surgeries. Okay, so n. How many times is the doctor going to do this surgery? He's going to do it 8 times because it's going to be on 8 patients. The probability that the surgical procedure is going to be successful is 85% or 0.85. So remember, Q is going to be 1 minus 0.85, which would be 0.15. Okay. And then X. Remember what X is going to stand for. The number of times that the surgical procedure was done correctly or successfully. So the doctor's going to do this on 8 different patients. It's possible that it wasn't successful on any of them. Or it's possible that it was on 1 or 2 or 3 all the way to 8, right? It's possible that all 8. So again, this here would also be binomial, right? Okay. All right. Okay, so let's take a look at the next one. Part C says a jar contains 5 red marbles, 9 blue marbles, and 6 green marbles. You randomly select 3 marbles from the jar without replacing them. The random variable represents the number of red marbles. Okay. So, let me get my pen. Oh, come on. Shouldn't be freezing. Okay, here we go. n is going to be, we're going to do this, what, I guess 3 times? Okay. So let's see, we're going to figure out what's the probability that we're going to get. It looks like we're looking for a red marble, right? Because the random variable represents the number of red marbles. So we have 5 red, 9 blue, 6 green. So it looks like the total number of marbles we have, 5 and 9 is, 14? 14 and 6, it looks like it's total of 20. Okay. So the first time that I get a red marble, because there's 5 of them, it's going to be 5 out of 20, right? But notice I'm not replacing them. So the second time I choose, if I want to get a red marble, now I'm only going to have 4 out of 19. And the third time that I choose, now I'm only going to have 3 out of 18. Remember we said the probability needs to be the same each time, and if you notice, it's not. So this here is not it's not a binomial experiment because my probability isn't the same each time. If I'm trying to get that red marble, my probability is changing. The reason being, guys, is it's without replacement. Okay. All right. So we have something called the binomial probability formula. And it says in a binomial experiment, the probability of exactly x successes and n trials is given by, and we got this formula here, probability of x equals ncx times p to the power x, q to the power n minus x, and it gives me all this kind of business right here, okay? And it says where n is the number of trials, p is the probability of success, q is 1 minus p, probability of failure, x is the number of successes and n trials, n minus x is going to be the number of failures, okay? Let's see. So let's see if we can figure this problem out here. It says a card is selected from a standard deck and replaced. The experiment is repeated a total of 5 times. Identify n, p, q, and x. Okay. Find the probability of selecting exactly 3 clubs from using the binomial probability formula. Okay, so how many times are we going to do this? We're going to do this 5 times. So n is going to be 5. Okay. So what I'm going to do real quick, guys, I want to make sure that we all understand what a deck of cards looks like. So I'm going to pause this and I'm going to pull up an image of a deck of cards. Okay, so we're trying to figure out what's the probability that we're going to get a clubs, right? So, okay, here's my deck of cards. So guys, this top row here, these are clubs, these are spades, these are hearts, and the last one is diamonds, okay? So we have 4 different suits, right? What's the probability I'm going to get a clubs? 1 out of the 4, right? So I'm going to come back over here, okay? Remember, 1/4 is the same thing as 0.25. So Q would be 1 minus 0.25 would be 0.75. And it says find the probability of selecting exactly how many clubs? 3. Okay, so now I'm just going to use my formula here. N is 5, so I'm going to go 5, choose 3. The P number is 0.25. Raised to the power of x. X is the number 3. Oops, that doesn't look like a 3, does it? Let's fix that. There we go. 3 times my Q number, which is 0.75, raised to the power n minus x. So n is 5. 5 minus 3, okay? 5 minus 3 is the same thing as 2, right? Okay, so let's do this on our calculator. So I'm going to get my calculator right here. Let me move it over this way, turn it on, clear it out. So remember how I'm going to do this. We did this in chapter 3. So I'm going to go 5, math, probability. I'm going to go down to the third one, choose 3, okay? And then I'm going to go times, I'm going to put this stuff in parentheses. So 0.25 to the power of 3 times 0.75 to the power of 2. You could have hit the little squared button if you wanted to. And I'm going to hit enter. And the number that I'm coming up with is 0.0878 or 79. I'll go 79, so 0.0879. 0.0879. And so here is my probability, okay? Let's see. Let's try the next one. We'll go about it doing it the same exact way. It says 63% of U.S. adults oppose special taxes on junk food and soda. You randomly select 10 adults. Find the probability that the number of adults who oppose special taxes on junk food and soda is exactly 6. Okay. So first thing we're going to do, we're going to go N, P, Q, and X. Those are going to be the first things we're going to find. Okay, so we're going to randomly select how many adults? 10, right? Okay, that's going to be my N. What's the probability that people oppose special tax on junk food and soda? 63%. So guys, remember, 63% is the same thing as 0.63, okay? So now remember, Q is going to be 1 minus 0.63. 1 minus 0.63 should be something like 0.37. And X is, we're looking for the number of adults who oppose special taxes on junk food and soda is exactly how many? Is exactly 6, okay? So now, I'm going to go ahead and go through my problem. So I'm going to say P of X, P of 6 in this case, is going to be NCX, so N was 10, choose 6, times the probability, which is 0.63, to my power of X, X in this case was 6, times Q, which is 0.37, to the power N minus X. Well, N minus X, 10 minus 6 will give me 4, okay? So again, I'm going to do this exactly like the way it did before on my calculator. I'm going to pull this up, and I'm going to go 10, math, probability, go down the third one, I'm going to choose 6, right, times, the rest I'm going to do in parentheses, 0.63, raised to the power 6, okay, times 0.37, raised to the power, 37, there we go, raised to the power 4, and I'm going to hit enter. So guys, I want you to notice whether I do the 4 inside or outside, in this case it doesn't particularly matter because the exponent is only going to what's inside the parentheses, right? So if I wanted to, I could do something like this. I could say, oh look, let's delete that. And we can put the parenthesis on the outside, but it's going to give me the same thing. And I'm coming up with 0.246 and 07, so I'd say 0.2461. 0.2461. Okay. Alrighty. Now we're going to talk about constructing a binomial distribution. And it says, recall that the random discrete variable x in a binomial experiment represents the number of successes and n trials. By listing all possible values of x with corresponding probabilities, you can create a binomial probability distribution. Okay, so let's see if we can figure this one out. All right, so this next problem here, guys, says 34% of voters think that Congress should help write standards for school food. Let's see, we're going to randomly select 6 voters and ask them whether Congress should help write standards. The random variable x represents the number of voters who think Congress should help to write the standards. We're going to create a probability distribution, okay? So I want you to notice here, they're giving me the formula, right? And guys, we use the formula for the other 2 problems, but I'm going to show you there's an easier way to do this using your calculator, okay? So guys, I'm going to do this on my calculator. So let me pull this up here. Let me clear it out, okay? The first thing I'm going to do, it tells me right here, we're going to start by hitting the second button and the vars, okay? And then I'm going to scroll down until I find something that's going to say Binomial PDF. So I'm going to keep scrolling. I got to scroll a little bit. Okay, so notice there's 2 of them. There's Binomial Cdf and there's Binomial PDF. I want the PDF, okay? So I'm going to click on that. And I want you to look down here. Right here, down here at the bottom, it says you can then change each entry one by one. It says Binomial PDF. It says the number of trials, comma, P, comma, X. Okay? So before I get started, let's see. Number of trials, we're going to select 6 voters. So N is going to be 6. My P is 34%, which would be 0.34. So then if P is 0.34, Q would be 1 minus 0.34, which would be 0.66. And then X is going to take on these values, 0, and we're going to keep doing this until we get to 6, right? Okay, so let me pull back my calculator again. All right, so the first part is N, the number of trials. And we said the number of trials we had was 6. And I'm going to enter a comma. My P, my probability, which in this case is 0.34. And then I'm going to enter in a comma. And then I'm going to enter in my first X value. You notice my first X value is 0. Okay? And I'm going to close my parentheses. I'm going to hit enter. And what this is doing, guys, it's actually doing this formula here for me without me having to write everything out. Okay? So I'm going to go to 4 decimal places. It looks like it's going to be 0.0827. So right here, I'm going to type in 0.0827. Okay? And then I'm going to do this process all over again. And now, instead of me putting X as 0, I'm going to hit X as 1. But instead of me having to type everything again, if I hit second and then the enter button, it types in everything I just typed in before. And where that 0 is, I just move my cursor back to it. I'm going to type in the number 1. I'm going to hit enter. And I'm going to keep going to 4 decimal places each time. So this one looks like it's going to be 0.25555. Okay? And so I'm going to keep playing this game. So I'm going to go second, entry. I'm going to change that 1 from a 1 now. I'm going to change it to a 2. 0.3290. 0.32, oops, 90, not 09, 90. Okay. And let's do this again. So second entry. Okay. Binomial PDF, right? I'm going to change that 2 to a 3. Okay. 0.225. Looks like it's going to be a 60, right? 0.2260. Okay. Let's keep doing this again. So again, if you want to know how did I get there to begin with, in case you missed it, second bars, scroll down till you find Binomial PDF, hit enter. The first part is the number of trials. That's my N. We had 6, comma, I need to put a comma. My probability, which was 0.34, comma. Okay, we just did 3. Now I'm going to do number 4. Okay, close my parentheses, hit enter. And I'm coming up with 0.0873. 0.0873. And again, so I don't have to do that each time. I can just hit second entry, change that 4 to a 5, hit enter. 0.0180, I guess. 0.0180. Remember, I'm rounding to 4 decimal places each time, okay? And one more time, we're going to change that 5 now, guys, to a 6. And I'm coming up with 0.0015. Okay. So you can kind of see right here, this is the process and how it's done. On the calculator app, guys, I just checked on my iPad. It's working exactly the same, okay? All right. So we did our probability distribution. And now it says, identify any values of the random variable x that may be considered unusual. They're considered unusual when the probability of those values is not equal to, but I should say is less than 0.05. So I'm going to look for any probabilities that are smaller than 0.05. So this is smaller, and that's smaller than 0.05. Okay, so those two there. So when x is equal to 5 and when x is equal to 6, right? Okay. All right, let me pause it. All right, So we got a couple of more problems here, guys, out of 4.2. And I'm actually going to go to problem number 6 first, because it's referring back to the problem that we just did with the Congress and the 34% of the voters and so on and so forth, right? Okay, so it says find the probability that exactly 3 voters think Congress should help. So if I come back over here and I say, what was the probability of 3? We came up with 0.2260. So for part A, I'm just going to type in 0.2260, right? Now, look at part B. It says find the probability that at least 3 voters think Congress should help. At least 3. What does that mean? At least 3 means that we should have more than or equal to 3. So it means that we could have 3 and 4 and 5, oops, and 6, right? So I'm going to take 3, which we already know, we wrote it down, 0.2260, and what was 4? Let me scroll back up to the top. 4 was 0.0873, 0.0873, and then 0.018, 0.018 with another 0, and then 0.00 something, I forgot what it was, 0.0015, okay? And, oops, get my pen back. Oh, come on. Why is this not wanting to work? There we go. 1.5. And I'm just going to add those numbers together. So let me grab my calculator again. Let's move it over this way. So 0.2260, oops, turn it on first, Omar. 0.2260 plus 0.0873 plus 0.0180 plus 0.0015, and I'm coming up with 0.3328. 3328. Okay. And then part C says find the probability that fewer than 3 should help. So fewer than 3, x is smaller than 3. If x is smaller than 3, that means that x will be smaller than or equal to 2. Okay? So what I'm going to do, guys, smaller than or equal to 2 would mean that now I would take these here. Okay? So I'm going to show you, there's a couple of ways I could do it. One way is I could take these 3 numbers and add them together, right? But remember, if I were to take all these probabilities and add them all up, I should be getting the number 1, right? Well, if I already know what this number is, and I want to find this one, in addition to adding those 3 numbers, another way I could do it is I could say, well, what's 1 minus whatever that sum was right there? And we just found that sum. So I would take 1 minus 0.3328. And so if I take my calculator right here, 1 minus 0.3328, I'm coming up with 0.6672, right? And we can double check and say, well, what happens if we were to add those numbers together? So let me move this over here. What happens if I decided to add 0.0827 plus 0.2555 plus 0.3290, 0.6672? Same answer, right? Okay, so just want to kind of show you, oops, where am I? That's how I'm sort of doing that problem, okay? And I'm going to do number 7, and then I'll come back and do number 5, because number 7 is pretty simple. And it's just, you know, you might have a problem like this in your homework where you're using a table and it says about 55% of small business in the United States have a website. You randomly select 10 small businesses. What is the probability that exactly 4 of them have a website? Okay, so if you notice here, here's my n is 10. I'm going to go to where the probability is 55. So here it is at 0.55, and here it is at 0.55. Okay, and now I want when it's exactly 4 of them. So these here, n is 2 and n is 3, so I'm not interested in that. I'm interested here And I'm going to kind of just do this. Boom, there we go. 0.160. So there's the ways you can do some of these problems, guys. You have a table. That's pretty much how you do it, okay? Alrighty, let's go back up to number 5. And number 5 says, a survey found that 34% of U.S. adults have hidden purchases from their spouses. You randomly select 200 adults with spouses. What's the probability that exactly 68 of them have hidden purchases from their spouses? Okay, so N, how many people did we randomly select? 200. Okay, what's the probability that they have hidden purchases? 0.34. Okay, we want to figure out the probability that exactly how many of them? 68. So if you notice right here, it tells me binomial PDF, number of trials, P, and then X. So I'm going to come back to my calculator, right? I'm going to move this over a little bit so we can see. How do I get to my binomial PDF? I'm going to hit second. Then I'm going to hit the VARs button, okay? And I'm going to scroll down until I find binomial PDF, okay? So look, it's number 10. And I'm going to hit enter. My number of trials was 200, comma, 0.34, comma, and the number 68. Okay, close that up, hit enter, and I'm coming up with 0.0595. If I go to 4 decimal places, 0.0595. Okay, boom, there we go. All right, so we got that part done. Now let's scroll back down, okay, and we have something here dealing with, let's see, mean variance and standard deviation. It says the same formula is used in 4.1 for mean variance and standard deviation can be used with binomial probability distributions. However, the following formulas are much simpler. So it says the mean is going to be equal to n times the p, the variance is going to be n times p times q, and my standard deviation will be the square root of that. Okay, so number 8 says, in San Francisco, about 44% of the days are clear. Find the mean, variance, and standard deviations for the number of clear days in the month of May, and interpret the results and determine any usual events. Okay, so how many clear days do we have? 0.44, right? How many days, if 44% of them are clear, how many are not clear? 56, right? Now, N is going to be the number of days during the month of May. Anybody know how many days are in the month of May? And if you say, you know what, I'm not really sure, then I'll tell you what we'll do. How many days are in, May? 31. Okay, right? So 31. Perfect. All right. So let's see. We're going to find the mean. So the mean is this mu. Okay, looks like a funny looking u. It's going to be n times p. So n in this case is 31. P is 0.44. So my mean is going to be 31 times 0.44. 31 times 0.44 is 13.64. Okay, so that's how many, on average, that's how many clear days we're going to have in the month of May. All right, let's find the variance. So the variance says we're going to take n times p times q. So I'm going to take n, which is 31, times p, which is 0.44, times q, which is 0.56. Okay. Why am I using a v? I'm supposed to be using sigma squared. Sorry, guys. Okay, looks like a funny looking O. So let's take 31 times 1. Okay, now we can multiply that times 0.56. Okay, and 7.6384. So 7.6384. So usually they ask you to do it to 2 decimal places, so we'll do that. And then my standard deviation is going to be the square root of the answer that we just got. So the way I'll do that is I'll just take second, the square root, of the second of my answer. Remember, the answer is right above the little negative sign. Close your parentheses, hit enter. And usually they ask me to go to one decimal place here. So I'm going to type in 2.8. So sigma is going to be 2.8. Okay. So again, just to understand what this means. On average, there's about 13.64 days. That's the number of clear days. And most of the days are going to be 13.64 plus or minus another 2.8. That's how many days we'll have. Okay. All right. Now, these next two problems say, what's the probability that less than 68 of them have hidden purchases from their spouses? Excuse me. So if I come back to the problem that we're dealing with the spouses, where was it? Here we go. Okay. So 34% of U.S. adults have hidden purchases from their families or from their spouses. We're going to select 200, okay? So let me come back. Let me just write some information out. So we said in this case, P was 0.34. My N was 200, okay? And we're now trying to find the probability that less than 68 of them, okay? Less than 68. So think of what that would mean. I would have to take the probability that none of them do, plus the probability that one of them does, plus the probability that two of them do, plus the probability that three of them do. And I would have to keep going all the way until I got to 67, because I want less than 68 of them. So guys, I would have to use that formula a whole bunch of times. So instead of me doing that, there's something called the Binomial Cdf. What CDF stands for, the C stands for cumulative. Remember when we did cumulative frequency and we were adding the numbers up? So what this formula will do for me Binomial CDF, what it'll do for me, number of trials, probability, and my X, it's going to add them all up until I get to 67, okay? So I'm going to show you how I'm going to do this on my calculator. I'm going to clear it out. I'm going to go to second, go to vars, scroll down. Remember, we said number 10 was PDF. Look at number 11, CDF, okay? So number of trials is 200, comma, my probability was 0.34, comma, and now we're going to stop at 67. So I'm getting everybody from 0 all the way to 67. And what it's going to do, it's going to add them all up for me. And I'm coming up with 0.4734. So 0.4734. That's going to be the probability that less than 68 of them, which would be 1 through 67, are keeping hidden purchases from their spouses. Now, there's a second part. What's the probability that 68 or more, right? So we just found the probability of 67 or less, right? We just found the probability that X was less than or equal to 67, okay? Now we want to know what's the probability that 68 of them or more. So if we already found the probability of 0, of 1, all the way to 67, and now what we're trying to figure out is what's the probability that 68, 69, all the way to 200 have them. Well, we can say, let's take 1 minus whatever we got from here, and that'll give me that answer. So I'm going to go 1 minus 0.4734. Okay. So 1 minus 0.4734, and that is giving me 0.5266. 0.5266. Oh, come on, pen. There we go. And that's going to be the probability that 68 of them or more have hidden purchases from their spouses, right? So again, I want you to notice something. CDF means it's going to add them all up for you already, right? And that right there, guys, is 4.2.